Welcome. This video is going to take a look at section 2 of chapter 3 and looking specifically at periodicity and the properties of the different elements. So the elements are organized on the table to show this periodicity or how their properties repeat regularly. And physical properties such as atomic and ionic radii and then electronegativity and ionization energy explain this periodicity of the chemical properties. So understanding the trends for these four physical properties is really key to understanding chemistry, and it really all revolves around the atomic size, either the atomic or ionic radii. And my mnemonic I like to keep in mind is lower left are the large losers. Okay, I'm talking about the periodic table here. The upper right is small and tight, meaning those elements are unlikely to lose electrons. So keep that in mind as we look at these next couple slides here. Another concept you have to have a firm grasp of to understand these trends is this idea of effective nuclear charge. We talk about full nuclear charge and effective nuclear charge, and think of it kind of like being similar to your paycheck. You have your gross pay, which would be your full pay if there were no taxes, and then you have your net pay, which is what you actually end up with because they take taxes and other things out. So full nuclear charge is equal to the atomic number, which is the number of protons. So it's a positive value equal to the number of protons. So that means the nuclear charge increases by 1 as you move up each element between successive elements. Element 20, positive 20. Element 21 increases by 1. Okay, so that part's pretty easy. Then there's this idea of outer electrons. And remember, outer electrons, which include your valence electrons, determine many of the properties. Well, these outer electrons don't experience the full attraction of the nuclear charge because there's all these inner electrons which shield them, okay? Think about like if you put a magnet on the refrigerator. If you have lots of paper, the attraction between your magnet and your refrigerator isn't as strong and the magnet starts slipping down. It's the same thing. The more layers of electrons between your nucleus and your outer electrons, the more shielded and the less that attraction is. So effective nuclear charge is the charge actually experienced by the valence electrons, and it's always less than the full nuclear charge, except for hydrogen and helium, which have no inner electrons, because of the shielding, and also there's some repulsion going on by the inner electrons. They're helping push those outer electrons even further away. So how do we calculate effective nuclear charge? It's considered to be roughly equal to the full nuclear charge minus the number of your inner electrons. So conveniently, this works out for the A groups that it's the number of your valence electrons or the number of your A group. So group 1 has an effective nuclear charge of 1. Group 2 has an effective nuclear charge of 2. The polyatomic ions, the transition metals, it gets a little weird as you go across here, but we're going to stick mostly with the A group. So group 13 has an effective nuclear charge of 3, and then 4, 5, 6, 7, 8. So for example, sodium is number 11 with 1 valence electrons. So you take that positive 11 minus the 10 inner electrons, and its effective nuclear charge is plus 1. Argon over on the other end, number 18, has 8 valence electrons. So its effective nuclear charge is going to be plus 8 because you can subtract the 10 inner electrons. So the trends in effective nuclear charge, as you go across a period, think about it, you increase your nuclear charge by 1, and yes, you also increase your electrons, but they're not inner electrons. So the effective nuclear charge will increase by 1 as you go across a period. When you go down a group, though, you have a big increase in both inner electrons and in the nuclear charge, but they happen to be equal increases. So the increase in nuclear charge is completely offset by the increase in inner electrons, so the effective nuclear charge remains the same. So group 1, all those elements, sodium, potassium, rubidium, they have the same effective nuclear charge. And again, it's equal to the group number or the number of valence electrons. Okay, so let's look at the first physical property, atomic radius. It's measured as half the distance between neighboring nuclei since the outer boundary of an atom isn't well defined. So you have to have two atoms near each other and see what the distance is between, because the assumption is that they will get as close as their clouds allow them to. It can be thought of the distance from the nucleus to the outer electrons, but if you remember Heisenberg's uncertainty principle, we can't ever actually measure this because as soon as you try and measure an atom, you disrupt where it's at and you move it. The IB data booklet shows atomic radii decrease across a period and increase down a group, so you see the two trends. Your job is to be able to explain why. Okay, so if you can't remember what the trend is, you can always look at the table, but then you have to be able to put the pieces together. Why does it decrease across a period and increase down a group? So again, here you can see the trend real easily when you look at this diagram down there. But if you think about it, increasing down a group makes sense because the number of electron shells increases. So physically, you are adding another floor or another layer to this atom's electron cloud. But the effective nuclear charge, remember, is staying the same. So the electron cloud and the atom are both going to get bigger. Going across a period, however, we're going to see a decrease in size, which this is the one that messes people up. Going down, sure, it should get bigger. I'm adding another shell. But going across a period, I'm adding stuff, and yet it gets smaller. How come? Because as you go across a period, remember that effective nuclear charge is increasing. The nucleus is getting stronger and able to exert a stronger pull on the electrons. You are adding electrons, but they're going into the same energy level. So now it's able to pull everything in closer. And in fact, the change in size as you go across from sodium to chlorine is pretty dramatic, from 186 to 100. And that's our first physical property.